to put this in two sections. Okay, our IPv6 address is in hexadecimal. Our MAC address is in hexadecimal. So when we put IPv6 address in hexadecimal on the computer, or when we see this MAC address in hexadecimal, we need to know how the computer sees this behind the scene. That is what is going to take us to another calculation, guys. So we want to learn how to convert from hexadecimal to binary. This hexadecimal, how do we convert it to binary? Because that is the language of the computer. Computer does not speak in hexadecimal. It does not speak in binary. In decimal. It only speaks in binary. So when the computer sees an IPv6 address, which is in hexadecimal, you guys that I was telling you guys that IP version full address is in decimal formats. By the time we come to IP version 6, maybe on Friday or next week, you will see that IP version 6 is in hexadecimal. So when you see, or when the computer sees that IP version 6 in decimal, in hexadecimal format, how does it interpret it in binary? That's what we want to do now. Or if we want to convert this MAC address into binary, how does the computer see in binary? That's what we want to do now. We want to take care of, we're taking care of decimal to binary and vice versa. Now let's take care of hexadecimal to binary. And this is one is even easier. So what you need to understand, when you talk about hexadecimal digits, we're talking about base 16. Look at it here, base 16. hexadecimal is base 16. Now, I like these parts. I like this. Look at what they wrote here. Hexadecimal and IPv6 address. To understand IPv6 address, take notes. For you to understand IPv6 address, you must be able to convert hexadecimal to decimal and vice versa. So we can go that direction as we are traveling now. Hexadecimal to binary or to decimal. You're going to see, I'm not going to take care of all the three. So this hexadecimal system is a base 16 numbering system using the digits of 0 to 9 and letter 8 to 7. Look at it in this place. Look at the hexadecimal digits here. It starts from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, which is equivalent to 10. B, which is equivalent to 11. C, which is equivalent to 12. D is equivalent to 13. E is equivalent to 14. F is equivalent to 15. So the last number here is 15. Why did they not call it base 16? I have told you, in IT, in the world of networking, 0 is a valid number. So the journey is starting from 0, and 0 is counted as the first digit. So when you say base 16, 0 to 15, that's 16. It's base 16. These are all our digits in hexadecimal. And even in this table they gave us, they have given us the binary value. Look at the binary value of 0 here. Look at the binary value of 1 here. Another thing you need to know, for each of these hexadecimal digits is equivalent to 4 binary digits. One hexadecimal digit is 4 bits. One hexadecimal digit is 4 bits. Take note of that. I'm going somewhere now. So look at 3. Look at the equivalence. 4 equivalence. 5 equivalence. 6 equivalence. And so on and so forth. So since I know that one hexadecimal digit is equivalent to 4 binary value, then I don't have a problem if I want to convert from decimal to hexadecimal or vice versa. So let's pick one of the numbers in hexadecimal. So if you were given something like, let's say 9 to convert to binary, how do you convert to binary? This is what you're going to get. It's the same thing we did earlier. Everything we did earlier. If you were given 8 to convert to binary, that means you will convert 10 to binary. If you are given B to convert to binary, that means you will convert 11 to binary. If you are given C to convert to binary, if you are given 30 to D to convert to, it's the same thing we did earlier. So let's pick one or two and use as an example. So let's assume I gave you A to convert to binary. So from that list we go given there, you and I know that A is equivalent to 10. What I'm simply telling you is convert 10 to binary. And in this scenario now, once you see OX and then I put A, even if I don't put AOX, once you see A, you know I'm talking hexadecimal. And what you know about hexadecimal digits will give you 4 bits. So you're not going to arrive at 8 in this scenario. So guys, let's start the journey. Same thing we did earlier. 10, put 2. Why are we doing 2? That's how we do it. We are going to binary. We're going to binary. 2 in 5. I mean 10. 5. Remainder 0. 2 in 5. 2. Remainder 1. 2 in 2. 1. Remainder 0. 2 in 1. 0. Remainder 1. And I'm done. I'll write from down up or down up. 1 0 1 0. That is equivalent to, hey, this is the binary value. What if you are given C? C is equivalent to, B is equivalent to 11. C is equivalent to 12. You convert 12 to binary. That one is very simple and straightforward. Once you know the number that is equivalent to a particular digit, if it is, they are not giving you normal number. What I mean by that is, let's say you were giving A or B or C or D or E or F. Just know the equivalence. Know the equivalence, then convert to binary. Convert to binary. What if you are within this range of 0 to 9? That one is even easier because I'm saying 9. So now, let me show you something here. Let me show you something here. So if I gave you 9 now, and I said, convert to binary. You know the first question you should ask me? Is it a decimal 9 or hexadecimal 9? Because if you are doing decimal 9, you're going to get 8 bits. If you are doing hexadecimal, you're going to get 4 bits. So how I'm going to differentiate this is I will put OX. That OX simply means it's hexadecimal you are dealing with. So once you see any number, digit between 0 to 9, and you are seeing OX, you are dealing with hexadecimal, not decimal number. And that means you're going to arrive at 4 bits. So put in what we have been doing earlier. We convert this to binary. 2 in 9, 4, remainder 1. 2 into 2, remainder 0. 2 into 1, remainder 0. 2 in 1, 0, remainder 1. That will give me 1001, and this is in base 2. So I've done A for you guys. I've done A for you guys. I have done, this is 9. What if you were told to convert this back to hexadecimal? It's very simple. The same thing we did with, what did you call, with our decimal. Just at this time around, the power will not reach 8. The power is going to be 0, 1, 2, 3, because we are dealing with only 4 bits. And then you expand this. Okay, the first one will give us what? 1 multiplied by 2 raised to the power 0. This will give us 1. The last one is what? 1 multiplied by 2 raised to the power 3. It will give us 8. 8 plus 1, we got 9. So what's the difference? When you are expanding this one will land on 3. Unlike the other one that landed on 7, 0 to 7, this is 0 to 3. That one is 8 bits, this is 4 bits. Let's pick another binary value there and convert to decimal and see. To hexadecimal and see. So let's pick one value there. Let's say E. E is 110. 110. Let's say E is 110. 1110, which is equivalent to E. That is A, B, C, G, E. That is equivalent to what now? I wrote it before. This is equivalent to 10. This is 11. This is 12. This is 13. This is 14. So E is equal to 14. Thank you. E is equal to, we're supposed to get 14. So 1110. So let's do the calculation. 1110. You were given this and you were told to convert this to hexadecimal. So the moment they mention hexadecimal, you know that you are going to go into base 16, which is going to be 2, yes, to hexadecimal. 0, 1, 2, 3. You and I know this side is going to give us 0 in the long run because of this 0 here. So this one here will be 1 multiplied by 2 raised to the power 1, which is going to be what? 2. The next one will be what? 1 multiplied by 2 raised to the power 2, which is going to give us what? 4. The last one will be what? 1 multiplied by 2 raised to the power 3, which is going to give us what? 8. 8 plus 4 plus 2. 8 plus 4 is 12. Plus 2 is what? Then we arrive at 14. And I can go back the other way again. 14 back into base 2. This is 14 hexadecimal, guys. And they are not going to even give you in form for, they will just say E. You now need to look, find out, oh, E is equivalent to 14. So you calculate 14, you take it to binary. So you take your 2 and put it, that's like we did before. 14 in 2, 7, remainder 0. Then you bring 2 again, 7 in 2, 3, remainder 1. Bring 2 again, 3 in 2, 1, remainder 1. Bring 2 again, 1 in 2, 0, remainder 1. I still get what? 1110, base 2. So it doesn't matter where I'm coming from. I will always get the same thing. So that's why I said, once you understand that first stage, converting from decimal to binary, this one is a walkover. It's just that this is in base 16. We're dealing with 4 bits, not 8 bits. Hexadecimal digit, each hexadecimal digit is 4 bits. 4 bits. 4 binary digits. Unlike decimal, that is going to give us 8 binary digits. Let me show you something, guys. What if I told you to convert 192 to hexadecimal? You are given 192. It will not make sense anyway. But let me assume I say convert this 192 to hexadecimal for me. What are you going to do? Just write out those binary digits we got before, which is 11 0 0 0 0 0 0. This is 1 2 3 4 5 6 7 8. This is 8 bits. Divide this into 2. Why am I dividing it into 2? Hexadecimal is 4 bits. Divide into 2. I am saying convert this to hexadecimal. I want to know the hexadecimal value of this 192. The 8 bit we got earlier. Break it into 2. This is our 8 bit we got earlier. Convert this right side to decimal. Convert the left side to decimal. What do I mean by that? Put this in base 2. Do as if you are going back to decimal. 0 1 2 3. 0 1 2 3. This side here is going to land on 0 in the long run. This other side, what will it give you? You cancel this one. 1 multiplied by 2 raised to power 2 will give me 4. 1 multiplied by 2 raised to power 3 will give me 8. 8 plus 2 is 12. Which alphabet or number? Which letter is equivalent to 12? A is 10. B is 11. C is 12. My answer will be C, O. On this side, I got C. On the other side, I got O. Not 0, guys. This is hexadecimal equivalence of this. When you split that thing into 2, deal with the first side first as if you are going back to decimal. Deal with the left side as if you are going to decimal. Put them together, and that is the equivalence. That is the hexadecimal equivalence here. So when you see hexadecimal digits, you should know what the computer is thinking. Let's pick this my MAC address, for example, C8. Now look at the next digit, or the next set of numbers there. You don't call this 34 because each number is a standalone in hexadecimal. You call it 34. 8E. The next one is not 49. If you say 49, then you are talking decimal. It's 49. 8A. EE. This is my MAC address. So we can decide now to convert all of this into binary. And if we like, we can convert something here to decimal. But we don't need that decimal because we are talking of how does the computer see this in binary. We are coming from hexadecimal. How does the computer see this in binary? We are coming from decimal. How does the computer see it in binary? So you must be able to convert from decimal to binary, hexadecimal to binary. And in case I tell you to cross border, convert from decimal to hexadecimal. Not a big deal. Move to binary first. Split that number into 2. Take care of the left. Take care of the right. Whatever you get, jam them together, and that gives you the hexadecimal digit. Did that make sense to you guys? Thumbs up, guys. That makes sense. You are good with this. Class rep said I'm speaking a language. Man, did you study mathematics or you teach mathematics? Thank you, guys. So down the road, you're going to say how we're going to connect these dots. Okay, I see. That's nice. That's nice, guys. So that's how you move in between. That's how you move in between. So let me see if you guys have any question on this.